You'll see that our aim for today is that we're going to be able to graph the solutions of basic inequalities. There's a word in there that I want to talk about before we even start with our work for today, and that's the word solutions. Okay, we all know what inequalities are, but that word solutions may be a little bit unfamiliar to us. So when we're talking about solutions mathematically, okay, when you're talking about solution in the real world, you're saying, oh, that's the answer. And I think that's what a lot of you have in your head about what the word solution means in math. So when you think about solution, you think about, oh, x is equal to 9, or oh, x is equal to 10, or x is equal to whatever it is equal to one very, very specific number. However, in math, solution is a little bit broader than that. It's not just a number. A solution, and this is the terminology that we're going to use to do this, a solution is the value or set of values that makes a statement true. So you're going to hear me use the word solution a lot throughout today, and I want you to think about how that may be different, thinking about this part that it says or set of values, thinking about how your idea of solutions may be a little bit different now that we're looking at some different types of problems today. First, we're going to start off, however, with some review of some basic inequality symbols. And we're going to look right here at this inequality symbol. This inequality symbol is the greater than symbol. So one thing that I want us to think about is A, make sure that we recognize the symbols, but also think about the interactions that the symbols can have with the various different things. So what I'm going to ask you to do here in a second is I'm going to ask you to draw a picture that represents something that you think is greater than something else. So I'm going to give you an example before you do your own. So for me, I have baseball on the mind right now. It's baseball playoff time. Both the Giants and the A's are in the playoffs. I think that's super exciting. So for me, I'm thinking to myself, well, who do I like better, the A's or the Giants? Now, I don't really want to hear a big response on this because I think most of you are going to disagree with me on this. But I live in the East Bay, and I find the A's to be a really interesting team because the A's are a lower market team, yet they're doing so well. They're kind of like the underdogs. So I kind of for the underdogs. So for me, I'm going to draw this picture. And I'm sorry that it's really... So the A's are better than SF. So I want a lot of you to think about this. And I want you to write a picture that represents something. You don't have to use baseball teams. You don't have to use the A's and the Giants. You could be like, ice cream is better than cake. I don't really care. Draw a picture to represent something that you think is greater than something else, and then fill in the written statement below. So for me, I'm going to fill this in writing the Oakland A's are greater than the SF Giants. So do your own. I'm going to give you about a minute. That way you can really illustrate something beautiful. So we can write a statement two different ways. It has the same relationship between the Giants and the A's. It's just said a little bit differently. So here we see that we have the SF Giants are less than the Oakland A's. It's the same thing. Either way, we're placing greater value with the A's. So now we're going to look at some real-world examples of some inequalities, just some very basic inequalities, very basic inequality statements. We're not going to get into inequalities that have operations inside of them yet today. Today we're just talking about graphing basic inequalities because there's going to be a lot to cover. So this first one, it gives us an example where Ricardo has completed more than 9 problems. So they've represented that with the inequality statement x is greater than 9. So the number of homework she has completed is greater than 9. First thing that I want us to do, so this is just a habit I want us to get into, realizing that we can write this inequality two different ways. So we're going to start with the original inequality, x is greater than 9. Or, just as we showed with our examples written on the other side, we can totally flip this around and make this 9 is less than x. Either way we want to think about this is totally appropriate. Most of you are going to feel most comfortable with having your variable on the left-hand side. That's going to make the most sense to you. But I want you to be in the habit of being able to flip it around without any problems. So the next question says, what numbers can it be? X is greater than 9. Ricardo completed more than 9 problems. What values could x be? Ian?
10 and above.
10. Give me another value. Sage? What else could it be? 11. What else, Kyrie? 12. What else could it be? Kevin? Boring. What else could it be, Emmanuel? 1,944. Yeah, that's what I'm talking about it. 1,944. Okay, any of these numbers. Now, we could continue to list numbers into infinity. We could be writing on our paper all day long, and we would never write every possible value that is greater than 9. So, in order to graph the solution, the set of all values that make this statement true, we're going to graph it. So we're going to start a number line down here. I'm going to start my number line in the middle here with 9, because that seems to be the center point of our work today on this particular problem. I'm going to add some other values there just to make my graph look pretty, and to also have some values that I can check this with later. This is what we call an open inequality. So I want you to write on this that we're going to call this an open inequality. And what an open inequality means is if we're thinking about this particular inequality, I noticed that nobody here said 9, that 9 was part of the solution. You're thinking about it, you're plugging it in, you're saying, is 9 greater than 9? No, it's not. So what we do is, we know that 9 is kind of our starting point here, but we know it's not part of the solution. So I put an open circle because this is an open inequality. It means that 9 isn't part of the solution. What about 9.1? Would that be part of the solution? 9.1 is greater than 9? What about 9.001? Yeah, 9.001 is going to be greater than 9. Okay, so everything up until the point where we hit that 9 is going to be part of the solution. So we put this open dot here, and then we just start shading everything that's part of the solution. We just get this nice little line going. 9.1, that's right next to that 9 would be part of the solution. 10, 10.1, 10.5, those are all part of the solution. 11, that's part of the solution. And as Ian said, anything that's 10 and greater. And so the way that we represent that this is going to be and greater, everything out into infinity, is we shade the line all the way out to the end, and then we put an arrow shaded on the end. And this is a representation of the entire solution to x is greater than 9. So it's a representation of every value that would make this statement true. Because we can't list every value. We can't list 9.001, 002, 9.003, 9.004. We would be listing into infinity. That's why we use a graph to represent the solution. Now we can check to make sure that we graph this correctly. The way that we can do this is we can pick one of these numbers that we've shaded over. I'm just going to choose 12. I'm going to put a little check next to it, representing that's my check. And then I'm going to go all the way back to the original inequality up here. X is greater than 9. I'm going to plug that 12 in. So I'm going to put in 12 is greater than 9. I'm going to check. Is that statement true? Is 12 greater than 9? Absolutely. Kip, yes. All right. Questions? Jadea.
So we could write down all the numbers on a number line. And then if it has a number, you put the number down and then just save the whole line.
We want to shade the whole line. Because everything is part of that solution. All of these numbers that we have shaded over the top of, including anything out into infinity, is part of that solution. Kyrie.
So if you have that same problem and you listed it to 100, you can just pick any number you want.
You can pick any number you want to check it. Any number you shaded over, you can put in to check. All right. Jalen.
What if it's what if it's equal sign and
We'll talk about it. We're going to get to one like that. All right. Ashley's net gain or loss, actually, looks like a net loss, was less than 3. All right. So we have the inequality statement that comes from this. -3 is greater than x. So we're going to first of all write this both ways, because a lot of us aren't going to feel really comfortable working with this the way it is. A lot of us are feeling a lot more comfortable about seeing it with the variable on the left-hand side. So this one's going to make a lot more sense for most of you. It says x is less than -3. So what numbers can it be? X is less than -3. Be very careful. Think about what those values of negative numbers mean. Sage, what could it be?
-1.
-1?
No.
So if you're having trouble with this, I would suggest for a lot of you it helps to just go ahead and create a number line. So put -3 on the number line. Think about your values. For some of you, this is going to make you think about what some of those values that may be. Okay, x is less than -3. Sage,
We can do
any
any number.
number.
-1,600.
All right, -1,600. What else? Viviana. -24. What else? Kevin. -4. What else? Ian.
-3.1.
-3.1. And we could go on and on and on and on. We could list these numbers again into infinity, and we would never write the complete solution to this particular inequality, because we can't. So one way we can visually represent it is with a graph of the inequality. So I have, again, this is what we call an open inequality, because if we think about it, we're looking at starting at -3, and we want to ask ourselves, is -3 part of the solution? Is -3 less than -3? Kip yes or kip no. Is -3 less than -3? No. So we're going to put an open circle to indicate that -3 is not part of the solution. Okay, it's like a little hole right there. We're really, really, really close, but it's not part of our solution. So we want to shade in all the values that are less than -3. So we shade over these other values that are less than -3. And we want to make sure that we shade an arrow at the end to show that we could go infinitely in this direction and we would continue to find numbers that are less than -3. We'll do a quick check by plugging in one of the values we shaded over. So I'm going to plug in -5. I'm going to go all the way back to the original. It's always good in these problems to go all the way back to the original. I'm going to write -3 is greater than -5. Kip yes or kip no. Is -3 greater than -5? If you have trouble thinking about that, I always think about it in terms of owing people money when I see negative numbers. I think to myself, would I rather owe somebody $3 or would I rather owe somebody $5? Owing somebody $3 is a much better position than owing somebody $5. So that's greater. All right. Last one. Ashley has at least $2. So x is greater than or equal to 2. We're going to start by writing it both ways. And I can flip it totally around. Again, most of you are going to feel more comfortable probably with this first one. But I want you to be in the habit of being able to switch it around. x is greater than or equal to 2. What numbers can it be? Sunny? Could be 2, because it's greater than or equal to. So that makes this one a little bit different. We'll talk about that in a second. Kyrie? 3. What else? Jalen? 2.1. Yep, that works. Kevin? 4. Justin? 10. Emmanuel? Huh? 1 billion. That's 1 and... Oh, hold on. I'm not going to put in the comma there because that's going to get confusing. That's 1, 2, 3. That's 1,000. 4, 5, 6. That's 1,000,000. 1, 2, 3. There's 1 billion. All right, 1 billion. So all of these numbers are part of the solution. Again, we could write infinitely the number of values that could be part of the solution. Now, the interesting thing about this one is that I heard Sunny say, and he's absolutely right, that 2 is indeed part of the solution. Now, how do you think, since 2 is kind of our starting point here, how do you think I can draw 2 as our starting point and make sure that it's clear to everyone that 2 is part of our solution? What do you think I could do, Iron? So we can take that circle that we had, and we can shade it in or close it in. So if the other ones earlier that did not have the number as part of the solution were called open inequalities, what do you think we call this type of inequality? Andrea? Closed inequality. So this is a closed inequality because in this particular case, 2 is part of the solution. It's also obvious. Every time we have the or equal to portion, that's a closed inequality. All right, so we have our shaded and dot proving that 2 is part of our solution. Now we need to shade over all of the values that are x is greater than 2. Which way should I be shading? To the right or to the left? Judea? To the right. All right, so I'm going to shade over it. I'm going to put my arrow on the end to prove that I know that I could shade this out infinitely in this direction and I would still run into values that are part of the solution. And then we want to check it. I'm going to check it by plugging in a value. I'm going to choose 5. Go back to the original inequality. 5 is greater than or equal to 2. And indeed, 5 is greater than or equal to 2. So this checks that we shaded the correct direction. Questions? Kevin? Kevin's actually jumping ahead to our key point. Were there any questions before we hit our key points? All right. All right, so we had one key point already talking about solution. So we should see now that these inequalities, their solution is a set of values. In fact, it's an infinite set of values. Okay? Kevin, what was your key point? Okay, so he's talking about closed inequalities. How do you recognize a closed inequality, Kevin? It has a shaded in circle, so that's how we graph it. When you saw the inequality itself, how did you know? Yep. They've got the or equal to portions on the inequality symbols. So I'm putting in parentheses, I know a closed inequality is less than or equal to or greater than or equal to. And I know that they are graphed with closed circles. And on the converse of that, open inequalities use the less than or greater than symbol. These are graphed with open circles. Other key points. Kyrie.
You can flip a inequality.
Perfect. All inequalities can be written two ways by flipping them around. All inequalities can be written two ways by flipping the sides and the inequality. All right. I think that's a pretty good set of key points for today. So I want you to move on to your